Control volume analysis. How do we do an energy balance for a control volume? And how do we analyze the performance of steady flow devices, such as turbines, pumps, and compressors? A control volume has been defined as a system in which both mass and energy can cross the system boundary. So in this control volume, fluid both enters and leaves the control volume. Heat can be added to the control volume, and work can also be done on the control volume. We want to calculate the flow rate of fluid into the control volume. The fluid is entering with a velocity v through a pipe which has cross-sectional area A. In some time interval dt, the fluid element enters with the length dx into the control volume. dx will equal v dt. The volume of fluid which has entered the control volume is therefore A dx. Since dx is v dt, we can write this as A v dt. The mass of fluid inside the control volume then is equal to the density rho times the volume AV dt. We can calculate the mass flow rate into the control volume, m dot, which will equal delta m by dt, and this is equal to rho AV. We can also write this in terms of the specific volume, which is given by the lowercase v and equals 1 divided by the density. The mass flow rate, m dot, therefore equals AV upon v, where A is the cross-sectional area of the flow, uppercase V is the flow velocity, and lowercase v is the specific volume of the fluid. At steady state, the mass flow rate into the control volume must equal the mass flow rate out of the control volume, and we will just denote that by m dot. Now, to do an energy balance, we have to calculate the flow work being done to push fluid in and out of the control volume. So the fluid element, which is entering the control volume, has a mass m, a pressure P, and a volume V. The force which has been exerted is F to push this into the control volume. The cross-sectional area is A. The length of the fluid element, which is about to enter the control volume, is L. And the pressure, which is resisting this fluid volume entering, is also P. Now the fluid volume has been pushed inside. The force required to push the fluid element into the control volume, F, is P times A. The work done in pushing the fluid element, W flow, is the force times the distance, FL, and this equals PAL. A times L is simply the volume of the fluid, so this is equal to PV. The work done per unit mass of the fluid entering is given by the lowercase w, and that would be the flow work divided by the mass of the fluid element. And that would simply be PV divided by M. And we can write that as PV, where the lowercase v is the specific volume. So now, at the entrance, we assume that the pressure is P1 and the specific volume is V1. At the exit, the pressure is P2 and the specific volume is V2. When the fluid both enters and leaves, there's energy P1 V1, which is carried into the control volume per unit mass of the fluid. At the same time, the energy P2 V2 is carried out of the control volume per unit mass of fluid, because this is the work which was done on the fluid element to push it out of the control volume. We can calculate the energy transported per unit mass of fluid. This would include the internal energy, U, because all fluid possesses internal energy, which it carries along with it. but it also includes the flow work, PV, because this is the work which is done to keep the fluid moving and it is carried as energy along with the fluid. The fluid has kinetic energy, half V square per unit mass, and it has potential energy, Gz, per unit mass. Now the first two terms we can combine in the enthalpy, H, which is U plus PV. And in flow problems, we always use the enthalpy H instead of the internal energy U because it includes the flow work. And this makes our calculation much easier. So the total energy transported per unit mass of fluid includes H plus half V square plus Gz. The advantages of using the enthalpy will become very evident when you do courses in fluid mechanics or heat transfer. So if you want to calculate, for example, the velocity field of fluid flowing in a pipe, what you would do is you would take an infinitesimally small control volume and do an energy balance on it as it moves along with the flow. Now, as it moves along, the surrounding fluid does work on that control volume, and the pressure varies in the flow field. So if you're using the enthalpy, that would account for the flow work. And from the energy balance, you can develop differential equations which you can solve to get the total velocity field. We can now account for all the energy transfer into and out of the control volume. So fluid is entering with a velocity V1, an enthalpy H1, and a specific volume V1. It leaves with the properties V2, H2, and V2. The height at the inlet is Z1, and that is measured from some arbitrary datum level. The height at the exit is Z2. There's work being done at a rate W dot, and there's heat transfer at a rate Q dot. We can write the rate at which energy enters along with the fluid. So H1 plus half V1 square plus Gz1 is the rate of energy transfer per unit mass of the fluid. We multiply that by the mass flow rate. So this term gives us the rate of energy transfer with the fluid into the control volume. Similarly, this expression, m dot times H2 plus half V2 square plus Gz2 is the rate of energy transfer out with the fluid. We can write a steady state energy balance. And at steady state, the rate of energy entering the control volume must equal the rate of energy leaving the control volume. So the rate of energy entering equals the heat transfer rate plus the power. Over here, we've assumed the sign convention that both of these terms are positive if the energy is being transferred from the surroundings to the control volume. Next, we write the rate at which energy is entering with the fluid, which is m dot times H1 plus half V1 square plus Gz1. On the right-hand side is the rate of energy leaving the control volume along with the fluid, which is m dot times H2 plus half V2 square plus Gz2. We can solve this so that on the right-hand side we have all the terms associated with the fluid, and that equals m dot times the change in specific enthalpy, the change in kinetic energy, and the change in potential energy. If we divide this equation by m dot, we can write it as Q, which is Q dot divided by m dot, and this would be the heat transfer per unit mass of fluid entering the control volume. Similarly, W is W dot divided by m dot, and this is the work done per unit mass of fluid entering the control volume. So this equation is our control volume energy balance. We can apply this energy balance to a control volume such as a turbine. In a turbine, the fluid enters at a high value of the pressure and the temperature, P1 and T1, with enthalpy H1. It leaves at a lower pressure and temperature, P2 and T2, with the enthalpy H2. Now we can neglect heat losses to the surroundings because turbines are usually well insulated. The changes in kinetic and potential energy between the inlet and outlet are usually negligible compared to the change in the enthalpy. So we can typically ignore those as well. We can write the energy balance for a turbine using our energy balance equation. We neglect the heat transfer, we neglect changes in kinetic energy, and we neglect the changes in potential energy. The shaft work done by the turbine then equals m dot H2 minus H1. Now the enthalpy at the exit is lower than the enthalpy at the entrance because the pressure and the temperature at the exit are lower, which means that W dot shaft is less than 0. And this makes sense because the turbine does work on the surroundings. We can also write an expression for the shaft work per unit mass of fluid going through the turbine. So that is W dot shaft divided by m dot, and that is simply the difference in enthalpy from the exit to the inlet. We can write a similar energy balance for a compressor. In a compressor, the gas enters at a low pressure with a low value of the enthalpy. It leaves at a high pressure with a higher value of the enthalpy. Again, we'll neglect heat losses to the surroundings and changes in kinetic and potential energy. Our energy balance can then be simplified by neglecting the heat transfer, the kinetic energy, and the potential energy. So the shaft work is equal to m dot H2 minus H1. In this case, since H2 is greater than H1, W dot shaft is greater than 0. And indeed, in a compressor, the surroundings do work on the compressor because we have to supply work to it to drive the compressor. We can do an energy balance for a pump, which is pumping an incompressible liquid. At the entrance, we have a low pressure and a low enthalpy. At the exit, we have a higher pressure and a higher enthalpy. The difference in height between the inlet and the outlet is delta Z. We are going to neglect heat losses to the surroundings, and typically changes in kinetic energy are also negligible. We're going to assume that the temperature T1 and T2 are the same, that there's really no heating up of the fluid as it goes through the pump. So if we start off with our energy balance equation, we can neglect Q dot, we can neglect the change in kinetic energy, and our energy balance becomes that the work done is equal to m dot H2 minus H1 plus G Z2 minus Z1. So the terms which we are looking at are the change in enthalpy and the change in potential energy. To calculate the change in enthalpy, we have the expression that for an incompressible liquid, H2 minus H1 is equal to C times T2 minus T1 plus V P2 minus P1. T2 minus T1 we've said is negligible. So we take the second term, V P2 minus P1, and we substitute it into our expression for the work. So the shaft work is equal to m dot V P2 minus P1 plus G Z2 minus Z1. So if we supply work to a pump, it can go into either increasing the pressure, P2 minus P1, or it can go to lifting the liquid up from Z1 to Z2. We can write energy balances for nozzles and diffusers. So in a nozzle, we enter with a velocity V1 and an enthalpy H1. We leave with a velocity V2 and an enthalpy H2. In this, we assume that the velocity V2 is much greater than V1 because that is the purpose of a nozzle, to accelerate the fluid. Now a diffuser is just a nozzle in reverse. So we are entering with V1, enthalpy H1, leaving at V2, enthalpy H2. But in this case, the exit velocity is much less than the inlet velocity. Now we can neglect changes in potential energy. We can neglect heat losses to the surroundings if the nozzle and diffuser are well insulated. And there's no work done in passing through a nozzle or a diffuser. We can start with our basic energy balance equation. The heat loss is negligible, there's no work done, and potential energy changes are negligible. So in this case, m dot would cancel out on both sides of the equation. And we are left with the expression that V1 square minus V2 square divided by 2 is equal to H2 minus H1. Now for a nozzle, V2 is much greater than V1. So let's assume that V1 is negligible, approximately equal to 0. In this case, the exit velocity from a nozzle is the square root of 2 H1 minus H2. For a diffuser, we are going to make the opposite assumption, that V1 is much greater than V2, and therefore V2 is approximately 0. So in this case, the inlet velocity V1 is the square root of 2 H2 minus H1. And we can use these expressions to calculate the inlet or the exit velocity for nozzles and diffusers. To summarize, we can write an energy balance for a control volume, which says that the rate of energy being added to the control volume must be equal to the rate at which energy leaves the control volume. The energy being added to the control volume has three components: the rate of heat transfer, the rate of work transfer, and also the rate at which energy is carried in by the fluid. The energy per output is the rate at which energy is carried by the fluid out of the control volume. For compressors and turbines, the rate at which shaft work is supplied to the control volume is equal to m dot H2 minus H1. For pumps, the rate at which energy is supplied through shaft work is m dot V P2 minus P1. This corresponds to the increase in pressure of the fluid, plus G Z2 minus Z1, which corresponds to the increase in potential energy of the fluid. For nozzles, the exit velocity V2 is the square root of 2 H1 minus H2. For diffusers, the inlet velocity V1 is the square root of 2 H2 minus H1.